To understand what is an integral and why is the area under a curve, we can actually start from a rectangle. Its width is delta x and its height is y1. The area is simply y1 times delta x. If we add a second rectangle with a new height y2, we just add the areas together. We can add a third rectangle, a fourth rectangle. Let's have 9 rectangles for now. We can write this total area using summation notation. Now let's overlay our curve, fx, going through all the y points. You can tell that the area of the 9 rectangles is similar to the area under the curve, but they are not exactly the same. To make them the same, we can introduce more rectangles. What if we double the rectangles from 9 to 18? The difference becomes smaller to 36 to 72 and eventually n rectangles. As n approaches infinity, the rectangles become infinitely thin. The total area of these infinitely thin rectangles is now perfectly identical to the area under the curve. If you were the first person to discover this, you'd want to create a mathematical notation as elegant and smooth as this process. Let's look at where the textbook formula actually comes from. First, let's rewrite the summation formula formally. We also know yi is just fxi. Now, we have the summation formula ready and we are ready to transform it into an integral formula. The first rectangle starts from x equals 0, but we can make it more general, say it starts from x equals a. The nth rectangle ends at x equals 9. To make it general, let's call it b. We can also rewrite the summation symbol into a smooth flowing s for sum. This is the integral fxi. We just need to get rid of the subscript I for simplicity. The width delta x, as it becomes infinitesimally small, we rename it dx. The limit of n approaching infinity is no longer needed because dx is an infinitesimally small width. And to integrate over the distance from a to b, it implicitly needs infinite steps. Now you have it. The definition of integral and why it's the area under the curve.